Hello and welcome. In this presentation, we will be showing how to create animations, and then storing them as movies files. The purpose of creating animation in Matlab is to learn signal processing, communications, AI, IT and controls conceptually, and how a system behaves with time. If these courses are of interest to you, please subscribe to the channel and share with your colleagues, friends and class fellows. Firstly, we will be presenting some of sinusoids. In addition to the fundamental frequency, we will be considering 5 harmonics of different amplitudes and frequencies. We also create a movie of each. Next, we will be plotting in 3D, and consider animation of chains to transform a 2D image into 3D for better illustration. Then the illustrations of how to create 3D animations with all the 3 axes changing at the same time. Then create a movie of each. Our third animation is about creating butterfly from curves, and the fourth animation is to generate a stopwatch which you can further extend to create an analog clock. If any of these codes is of interest to you, please drop a comment with email. Here we consider plotting sinusoids individually as well as their sum. The practice here is useful for Fourier series and Fourier transform, which are the workhorse of signal processing analysis. Firstly, we create 2 sinusoids x1 and x2. Of the same 10 Hertz frequency, these have amplitudes of 4.5 and 7.2, while the phase shifts are 35 and 80 degrees, respectively. The blue is x1, red is x2 and the sum is in light gray color. We can generalize the summation through a relation as shown. An elementary case could be to simply have the sum of 2 sinusoids as shown previously. Next we show a plot for the case of x of t equals 3 cosine of t plus 4 sine of 3 t. In the last 2 cases, a, n equals b, n equals unity. Please see that amplitude and the peaks of the resulting sums. The amplitude increase when we increase the number of harmonics in such a way. The 2 plots are the same except the first one sum 4 sinusoids of which 3 are harmonics and the second has 7 harmonics. We consider the animation for sum of sinusoids to see how the sum evolves with time. This is extremely important to see how a composite signal is affected by a given harmonic of some amplitude, phase, or frequency. In the Matlab code, we have 3 segments. The first code segment is the initialization. We create a time array for 0.2 seconds, set the amplitude and phase of each signal. Then we generate 5 signals, x1, x2, x3, x4, and x5 with frequencies of 10, 20, 30, 40 and 50 Hz, respectively. We then add all the signals to create a composite signal X. The second segment is loop, in which we clear the figure in each iteration. We plot x1, followed by its current sample. We repeat for x2, x3, x4 and x5. We finally plot the sum or composite signal and its lollipop, or stem version. The Matlab getFrame function is used to get a snapshot of the figure and saved in the variable mvec. After the loop, the frames are written to a video file as can be seen. The output video is seen next. Here, the amplitudes of all the signals are set to 5 with 0 phase shift. It can be seen that, at t equals 0, 0.1, and 0.2 seconds, all the signals are added constructively, and we have the maximum amplitude of the composite signal. As we move away from these times, the destructive interference increases, and the sum signal has smaller amplitude. In the next animation, we kept the amplitudes as 5, 2, 1.5, 1 and 0.5. The phase shift is 90 degrees and the frequencies are set as previously. It can be seen that the peaks of the composite signal shifted and the peaks at t equals 0.75 and 0.175 seconds, where all the signals are added constructively, and we have the maximum amplitude of the composite signal. Fundamental and first 2 harmonics effects are more prominent due to their large amplitudes. In the next animation, we have increased the amplitudes of the higher order harmonics. The amplitudes are 5, 0.5, 1, 1.5, and 2. The frequencies are set as previously. The phase shift is 0 degrees. The effects on the composite signal can be seen. In this animation, we have kept the amplitude of x1 as 5, while the odd harmonics are selected for all the remaining signals with amplitudes of 2 and the frequencies set are 10, 30, 50, 70 and 90 Hz. In this case, the composite signal has both positive and negative peaks at t equals 0, 0.05, 0.1, 0.15 and 0.2 seconds. In this animation, we have set the amplitude of x1 as 5, while the even harmonics of amplitude 2 are selected. The fundamental frequency is 10 Hz while the frequencies for the harmonics are set at 20, 40, 60 and 80 Hz. In this case, the composite signal has inverted peaks of the odd harmonics case at t equals 0.05 and 0.15 seconds. Finally, we have kept the amplitudes of x1 as 5, x3 as 10, while even harmonics of amplitude 2 selected. The frequencies set are 10, 20, 40, and 60 Hz. In this case, x3 has prominent effect in the composite signal. As a comment, one can apply different phase shifts and amplitudes while keeping all the signals of the same frequency. This would simulate a communication scenario where the same signal is received through direct and reflected paths. The phase shift would simulate the path delays, while the random amplitudes would simulate the losses in the paths where reflections and absorption occurs. The composite signal would be a distorted version of the original signal. In the second animation, we consider drawing 2D chains with a 3D view. In the Matlab code, again we have 3 segments. The first code segment is the initialization, in which we create a time array corresponding to 3 rounds. The number of rounds is multiple of 2 pi. We can adjust the radius or axis for an elliptical path. In the first instance, we draw the horizontal plane curve and then the vertical one. Next we draw the pointwise curves of both these curves as shown by the moving stars. The Matlab getFrame function is used to get a snapshot of the figure and saved in the variable mvec. After the loop, the frames are written to a video file. We use a video writer object to create a video file from an array or Matlab movie. The object contains information about the video and the properties that control the output video. Set the frame rate to 20, followed by file handler for the video. Write the snapshots to file and then close so that other applications can use it. The output videos for different rounds or cycles are shown next. The first animation is for a single round, the second for 2 rounds, and the other 2 are for 3 rounds. However, the top right has different values for the major and minor axes, resulting in elliptic paths. In this animation, we insert a sphere using the command, x, y, z, equals sphere. This is written in the initialization part. In the loop, we use surf command to plot the sphere. Note that each axis value is doubled to get an optional bigger sphere. In Matlab, the globe command is also available, which would help if one want to simulate the motion of a satellite around the Earth. This is Matlab code for 3D animation with time-based changing view. The first code segment is the initialization, in which we create a time array of 400 samples. We consider sine versus cosine functions for plotting circles and ellipses by adjusting the radius or axis. We choose z-axis as the time axis, so we get the variation along the z-axis. In the first instance, we draw the complete curve in 3D. Next, we draw the pointwise curve. For getting the snapshot and writing to a video file, the procedure is the same as mentioned earlier. The first video animation shows a circular path with radius of 5 for both the x and y axes. The second animation corresponds to x-axis or minor axis of 2 and y or major axis as 5. The path is 1½ round. The 3D view change with time as well. Here, the first video animation shows the x-axis or minor axis of 5 and y-axis as 1. We are not changing the view, that is, we comment the view command of Matlab. The other animations are for circular paths with changing 3D view as function of time with 1.5 and 4 rounds respectively. In the last animation, the color and marker are also changing with time. Our third animation is generating a butterfly as 2D curve as given in the initialization portion where the variable x is specified as a function of time using exponential, sine and cosine functions. The time axis is generated from multiple of -2 pi to 2 pi. For -4 pi to 4 pi, it generates 2 curves of butterfly while -24 pi to 24 pi generates 12 curves as shown in the figure. The Matlab command, polar, plots the butterfly using the parameters t and x as formed in the initializations section. Here, we show butterflies formed from 2 and 8 curves. The 2D animation is generated using the view command using time as one parameter. The last animation is stopwatch. We generate 2 circles starting from 90 degrees. One is the external unit radius circle for the digits and the second is 0.05 unit circle for the compass tail. The first loop is used to put text on the external circle. The animation is as shown, for which, the second loop is used to rotate the compass on each digit with a moment of 30 degrees. Hopefully, you have enjoyed the video, and has contributed to or refreshed your knowledge of creating animations and movies in Matlab. Please like, subscribe and share with friends and colleagues.